Imagine you're a scientist in 1905. You peer through your microscope at a drop of water, and you see something absolutely impossible. Tiny grains of pollen are dancing, jittering, moving in random, jerky motions like they're alive. But here's the thing, it's not just pollen. Ground-up rocks do it too. Dust particles, even fragments of glass. Dead matter dancing like it has a mind of its own. For almost a century, this phenomenon baffled the greatest minds in science. Nobody could explain it. But then, a 26-year-old patent clerk named Albert Einstein looked at this chaotic jittering and saw something nobody else did, a way to prove that atoms actually exist. This is the story of how the invisible became visible, how randomness revealed order, and how one man's genius turned dust into proof of reality itself. Let me take you back to the early 1800s. The year is 1827, and a botanist named Robert Brown is doing something that seems pretty ordinary. He's examining pollen grains under a microscope. Brown takes grains of pollen, suspends them in water, places the slide under his lens, and watches. What he sees stops him cold. The pollen grains are moving, not drifting, not flowing, but jittering rapidly, changing direction constantly, moving in completely unpredictable zigzag patterns. It looks almost alive. Now, at first, you might think, well, pollen comes from living plants, maybe there's some life force here. But Brown was a scientist. He had to test that assumption. So he repeated the experiment with completely inorganic matter. Finely ground rock dust, pulverized glass, dead, lifeless materials that had never been part of anything living. And guess what? The exact same motion. The rocks danced just like the pollen. This motion was real. It was reproducible. Anyone with a microscope could see it, but nobody, and I mean nobody, could explain it. Scientists threw out theory after theory. Maybe it was tiny currents in the water. Nope. Experiments in perfectly still fluids showed the same thing. Temperature irregularities? Tested and ruled out. Vibrations from the lab equipment? Same result even with perfect isolation. One by one, every reasonable explanation crumbled, and this motion, which became known as Brownian motion, remained one of science's most frustrating mysteries. But there were clues hidden in the chaos. Over decades of observation, scientists noticed patterns. First, smaller particles danced wildly than larger ones. Tiny specks went absolutely crazy, while bigger particles moved more sluggishly. Second, temperature mattered. Heat up the water and the jittering intensified. Cool it down and the motion slowed. Third, the thickness of the liquid played a role. Particles in thin, runny liquids moved more dramatically than those in thick, syrupy ones. Every single one of these clues pointed in the same direction. Down. Down to scales too small to see. Down to the world of the invisible. An idea started to emerge. What if the visible particles weren't moving on their own? What if they were being constantly bombarded by something invisible, something like molecules? But here's the problem. In the late 1800s and early 1900s, atoms and molecules were still controversial. They weren't proven facts. They were hypothetical concepts, useful for calculations, sure, but actually real? That was still up for debate. The skeptics had a point. Nobody had ever seen an atom. Nobody had measured one. Nobody had proven they existed. Until 1905. That's when a young physicist working in a Swiss patent office looked at Brownian motion with fresh eyes and saw something everyone else had missed. Albert Einstein realized something profound. Brownian motion wasn't a nuisance to be explained away. It was a window. If atoms were real, Einstein reasoned, then a pollen grain suspended in water would be constantly struck by an enormous number of invisible water molecules. Each collision would be tiny, random, far too small to observe individually. But in the wandering of the visible pollen grain itself, maybe there was a pattern, a statistical signature that reflected the invisible atomic bombardment happening underneath. The problem was this: if you watch any single pollen grain under a microscope, its path looks completely random, pure noise. Every trajectory is different. No two paths ever repeat. The exact zigzag is fundamentally unpredictable. So Einstein stopped trying to predict individual paths. Instead, he asked a different question. How do you describe random motion quantitatively? How do you find order in chaos? And here was his brilliant insight. Randomness doesn't mean lawlessness. Even when individual paths are unpredictable, collections of paths can obey precise statistical laws. It's like flipping a coin. You can't predict a single flip, but flip 1,000 times and you'll get very close to 50-50. Einstein focused on these statistical laws, and to understand them, he started with the simplest possible model, the random walk. Picture this: you're standing on a perfectly straight road. You flip a coin. Heads, you step forward. Tails, you step backward. Flip, step, flip, step. No strategy, no memory, no bias, just pure chance. This is called a random walk, and it seems almost too simple to be useful. But this toy model captures the statistical essence of Brownian motion. Here's why. A pollen grain jittering in 2 dimensions can have its motion broken down into 2 independent components, movement in the x direction and movement in the y direction. If we can understand the statistics of a 1-dimensional random walk, the full 2-dimensional motion follows automatically. So let's ask a simple question. If you take 200 random steps, where do you end up? You could be 200 steps forward or 200 steps backward, but that would require flipping 200 heads in a row or 200 tails in a row, extraordinarily unlikely. Maybe you'd end up right where you started. That sounds reasonable, since forward and backward are equally likely. But intuition isn't enough. To really understand what happens, we need to run the experiment many times. So imagine not 1 walker, but 500 walkers, all starting from the same spot, all following the same rules, but each making their own independent random choices. What happens? Some drift right, some drift left. Each traces its own unique path. And when we track all 500 at once, something beautiful emerges from the chaos. Instead of following individual walkers, let's divide the road into regions, bins, if you will. At any moment, we simply count how many walkers are in each bin. This gives us a histogram, a distribution of positions. And when we run the experiment with our 500 walkers taking 200 steps each, 2 striking features appear. First, the distribution is perfectly symmetrical around the starting point. This makes sense. Forward and backward steps are equally likely, so the walkers spread out evenly in both directions. Second, as time goes on, the distribution spreads out. The histogram gets broader. More walkers end up farther from home. And here's what's remarkable. At any stage, the distribution is beautifully described by a smooth, bell-shaped curve, a Gaussian distribution, centered on 0 displacement. This tells us that if we average all the positions of all the walkers, we get 0. Mathematically, we say the expectation value of position is 0. But here's the key. What changes is the width of the distribution. Take fewer steps and the Gaussian gets narrower. Take more steps and it spreads wider. And it's this spreading, not the average position, that contains the real physics. Einstein realized he needed a quantity that measured not where particles were on average, but how spread out they were. The problem with using average displacement is that it always vanishes. Forward wandering and backward wandering cancel exactly. The center of the distribution stays fixed, even though the particles themselves are constantly moving. So Einstein focused on something different, the squared displacement. Squaring removes the sign. A displacement of -3 and a displacement of +3 both give a squared displacement of 9. Now, leftward and rightward motion contribute equally. When you square every walker's displacement and average them, you find something beautiful. The mean squared displacement is proportional to the number of steps taken. Double the number of steps, and the mean squared displacement doubles. It's a perfectly linear relationship. Now comes the crucial conceptual leap. If a pollen grain's motion can be thought of as a sequence of tiny, uncorrelated steps caused by molecular collisions, then the number of steps is simply proportional to time. More collisions means more steps. More steps means more mean squared displacement. So, if mean squared displacement is proportional to the number of steps and the number of steps is proportional to time, then mean squared displacement must grow linearly with time. We can write this as mean squared displacement equals some constant multiplied by time. That constant controls how quickly the spreading occurs. We call it the diffusion coefficient, represented by the letter D. A larger D means faster spreading. A smaller d means slower spreading. When you work through the detailed mathematics, it turns out the relationship is mean squared displacement equals 2d times time. That factor of 2 isn't arbitrary. It falls naturally out of the Gaussian mathematics. But Einstein wanted more than just a descriptive law. He wanted to calculate d itself, to express it in terms of ordinary measurable properties like temperature, the thickness of the liquid, and the size of the particles. And remarkably, in doing this, he would find a way to count the number of atoms in a mole of substance. He would build a bridge between the macroscopic world we can see and the microscopic world we can't. His route across that bridge was subtle and ingenious. First, he treated Brownian motion as a diffusion process. We've already covered that part. Second, instead of attacking Brownian motion head-on, Einstein started with a system whose behavior was already well understood, the ideal gas. By the late 1800s, physicists like Maxwell and Boltzmann had shown that the properties of gases could be explained if they were made of tiny molecules obeying Newton's laws. Einstein's aim was to borrow that insight and apply it to jittering Brownian particles. The crucial step came from a Dutch chemist named Jacobus van 't Hoff, who showed that a dilute solution, like particles suspended in water, exerts an osmotic pressure that follows the same mathematical form as the ideal gas law. Einstein made a bold assumption. This same osmotic pressure law applies to suspended Brownian particles. With that single assumption, he could treat a Brownian suspension like an ideal gas and connect its random wandering to measurable properties. Here's where Einstein's genius really shines. He introduced an external force acting on the particles. Now, it's not immediately obvious why you'd do this, but Einstein wasn't interested in the force itself. He was using it as a tool. When you apply a constant force to particles in a fluid, two things happen. First, the force causes a drift. Particles flow in the direction of the force, creating what we call a drift current. Second, this drift creates a concentration gradient. More particles pile up in one region than another. And wherever there's a concentration gradient, diffusion kicks in. Particles naturally spread from high concentration to low concentration, creating a diffusion current in the opposite direction. In equilibrium, these two currents perfectly balance. The drift current and the diffusion current cancel each other out. This is Einstein's dynamical equilibrium condition. Now Einstein could calculate both currents. The drift current comes from Stokes' law, a well-known formula describing how spherical particles move through viscous fluids. The diffusion current comes from Fick's law, which describes how concentration gradients drive flow. When he set these two currents equal and worked through the algebra, something magical happened. The external force, the very thing he introduced to make the problem solvable, canceled out.
It gracefully bowed out of the equation, leaving behind a beautiful expression for the diffusion coefficient in terms of measurable quantities: temperature, viscosity, and particle size. Let's bring all the pieces together. We found that mean square displacement equals 2d times time, where d is the diffusion coefficient. We also found that d equals RT divided by 6 pi a times NA, where R is the gas constant, a known value from thermodynamics, T is temperature, easily measured, eta is viscosity, measurable in the lab, A is the particle radius, visible under a microscope, and NA is Avogadro's number, the number of atoms or molecules in 1 mole of substance. Combine these and you get Einstein's famous equation. Mean square displacement equals RT divided by 3 pi eta A NA times time. This is the wow moment. Every symbol in this equation except one can be measured with ordinary laboratory equipment. You can track particles under a microscope. You can measure temperature, viscosity, and particle size. There's only one unknown left, NA. And NA isn't some adjustable parameter you can tweak. It's a fundamental constant of nature, the conversion factor between the human scale world and the hidden microscopic world of atoms and molecules. Einstein had done something extraordinary. He had found a way to count the invisible by watching something visible. Einstein's theory was brilliant, but theories need experimental confirmation. That confirmation came a few years later through the meticulous work of French physicist Jean-Baptiste Perrin. Beginning in 1908, Perrin conducted a series of precise experiments. He used carefully prepared suspensions of nearly spherical resin particles in liquids with known viscosity. He would record a particle's position, wait a fixed time, record it again, and repeat, building up detailed maps of Brownian trajectories. He calculated the mean square displacement across many particles and showed that it grew linearly with time, exactly as Einstein predicted. Then, using Einstein's equation, he solved for Avogadro's number. His result? Approximately 6 times 10 to the 23rd, remarkably close to the value we know today, 6.022 times 10 to the 23rd. In his 1909 article titled Brownian Movement and Molecular Reality, Perrin wrote, "I think it will henceforth be difficult to defend by rational arguments a hostile attitude to the molecular hypothesis. The debate was over. Atoms were real." Perrin would go on to win the Nobel Prize in Physics in 1926 for his work on the discontinuous structure of matter. Einstein's work on Brownian motion was just one of 4 groundbreaking papers he published in 1905, a year often called his annus mirabilis, or miracle year. In March, he explained Brownian motion and proved atoms exist. In June, he published his work on the photoelectric effect, showing that light behaves as particles, work that would eventually win him the Nobel Prize. In September, he introduced special relativity, forever changing our understanding of space and time. And in November, he derived E equals mc squared, arguably the most famous equation in all of physics. All of this while working as a patent clerk. The Brownian motion paper often gets overlooked in favor of relativity and E equals mc squared, but in many ways it was just as revolutionary. It took something that seemed like meaningless chaos, dust dancing in water, and revealed it as proof of the fundamental building blocks of reality. Einstein himself said, "There are 2 ways to live. You can live as if nothing is a miracle. You can live as if everything is a miracle." When you understand Brownian motion, you see the miracle in the mundane. You see that a speck of dust floating in a sunbeam isn't just drifting, it's being bombarded by trillions of invisible molecules every single second. You see that randomness and order aren't opposites, they're partners in one of nature's most beautiful dances. You see that the invisible world is just as real as the visible one, and that with the right tools and the right insight, we can reach across that boundary and touch it. So here's to living as if everything is a miracle. Here's to the curiosity that sees mysteries in dancing dust. And here's to the genius that transforms those mysteries into proof. Thanks for watching. If you enjoyed this video, hit that like button, subscribe for more stories from the history of science, and let me know in the comments what other scientific mysteries would you like to see explained. Until next time, keep questioning, keep wondering, and keep looking for the miracles hiding in plain sight.